Welcome to Stoichiometry, probably one of the most important concepts in all of chemistry. Okay? It essentially asks the question, how much of this, meaning one reactant, reacts with how much of this, the other reactant. Okay? Now this could be several reactants, but we'll keep it simple and just have two reactants. The best way to explain this is using an example. Okay? Here is a visualized example of a chemical reaction. We can notice that it's balanced because we see coefficients here. 2 sodiums plus Cl2 goes to make 2 NaCl. And really, once again, balancing chemical equation just follows the law of conservation of mass. The law of conservation of mass states that mass cannot be created or destroyed. Okay. So if we start with 10 moles of sodium, each of these circles represent 1 mole, not one sodium atom, 1 mole, but you can think of it like 1 sodium atom, and each of these diatomic gases, 2 atom gases, represent 1 mole of chlorine gas. Okay, and finally we have the product. Okay, and stoichiometry is really asking us how much of this and how much of this will produce how much of this. So in this case, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 moles of sodium. And we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 atoms of chlorine, but 5 molecules of chlorine gas. Okay? And so the end product, we want to figure out how much of sodium chloride do we produce. Well, let's think about it. If we look at the molecular formula, each element, each sodium chloride, each salt compound has a sodium and a chloride. So you might have, I'll say the clear circle is sodium, and the colored in circle is chloride. Okay, sodium chloride, you have sodium chloride 1, 2. Okay, so we can cross out these, and if when you do this, you'll figure out that I won't draw all of them, but you'll figure out that you can have 10 of these, 10 moles of sodium chloride. Now you can think of these as 10 molecules of sodium chloride. Okay, 10 compounds of sodium chloride, but really they're 10 moles because each of these dots represent 1 mole. That's basically stoichiometry. You know, the ratio of sodium to chlorine gas is 2 to 1, and we see here that we produce sodium chloride. Or another way to put it, for every 1 mole of chlorine gas, you produce 2 moles of sodium chloride, which makes sense. We have 5 moles, we produce 10 moles. So for every 5 moles of chlorine gas, we produce 10 moles of sodium chloride. And when we look at sodium and the product sodium chloride, for every 2 moles of sodium, we produce 2 moles of sodium chloride. What does that mean? That means, well, simplifying it, for every 1 mole of sodium, we produce 1 mole of sodium chloride, which makes sense. We have 10 moles of sodium, we have 10 moles of sodium, and we produce 10 moles of sodium chloride. So that's really stoichiometry. But how do you do that using, a more skeleton equation, without pictures or anything like that? Well, we see here, we have an equation and it's balanced. Remember, when we're ever doing stoichiometry, always balance it. Always balance. It must be balanced, right? Because only when we balance it, we know how much of what reacts with how much of what, okay? When we balance it, we know that 1 mole of chlorine gas reacts with 2 moles of sodium atoms, okay? Because these 2 atoms pair and these 2 atoms pair to make 2 sodium chloride molecules, sodium chloride compounds. So we need to balance it first in order to carry out stoichiometry. And the second thing to always remember is always work in moles. So always convert to moles. Okay? Now the first example we'll do is when they give you moles. Okay? Let's say you have 1 mole. Well, let's ask this question. If you have 2 moles of iron oxide, how many moles of carbon do you have to react completely with iron oxide? And the answer is 3 moles, right? because look at for every 2 moles of iron oxide, for every 2 you can think of it as for every 2 molecules of iron oxide, you need to react with 3 molecules of carbon, right? Well, 3 atoms of carbon. Okay, so that's how you do it. What if you had, 1 mole of iron oxide? Okay, what if you had 1 mole of iron oxide? Well, when we had 2 moles of iron oxide, we needed 3 moles of carbon, right? Because in this equation, we see that for every 2 compounds of iron oxide, we need 3 atoms of carbon. Okay, so that means for every 2 moles of iron oxide, we need 3 moles of carbon. Moles is just, number of particles, right? And more specifically, 6.02 times 10 to the 23. But it doesn't matter if it's 20 particles, if it's 10 particles. If for every 2 particles you need 2 particles of iron oxide, you need 3 particles of carbon. Then if you need 2 moles of iron oxide, you need 3 moles of carbon. So what if you had 1 mole of iron oxide? Well, you need 1.5 moles of carbon, right? Half as many moles, half as many particles means half as many of the other particles. Okay? What if we had 4 moles? Well, simply we would just have, so if we have 4 moles, then we just need 6 moles, right? Because when we had 2 moles, we need 3 moles of carbon. Okay? So what you end up and this is basically the basis of stoichiometry. It asks, okay, I have this many moles, and remember, it's always in moles. And it wants you to know how much of this do you need, and how much of this will you produce. Okay? So let's say I have 2 moles of iron oxide. The question is, how many moles of carbon dioxide will we produce? Okay? And the answer is 3. Why? Because for every 2 moles of iron oxide, we produce 3 moles of carbon dioxide. And how much iron will we produce? We'll produce 4 moles. Because for every 2 moles of iron oxide, we produce 4 moles of carbon, right? And the reason for that is for every 2 particles of iron oxide, we produce 4 particles of iron. And so when you change that to moles, it's still the same. What if we had 4 moles of iron oxide? We would produce 6 moles of carbon. We would produce 6 moles of carbon dioxide, and we would produce 8 moles of iron. Okay? And the reason for that is iron has a coefficient of 4. Okay? So the ratio of the amount of iron produced over the amount of iron oxide is equal to 4, because you have a coefficient of 4 over here and over 2. So 2. And this is called the mole ratio, right? So for every molecule of iron oxide we produce, we will react, for every molecule of iron oxide we react, we will produce 2 molecules of iron. Okay? So that's the mole ratio. What about carbon to iron oxide? Okay? Let's say carbon to iron oxide. Okay? For every 3 molecules of carbon, we need to react it with 2 molecules of iron oxide. And keep in mind these mole ratios, you can put them any which way. This is just as correct as this, okay? Now they're not equal, okay? They're definitely not equal, but this iron oxide over carbon is equal to 2 over 3, and carbon to iron oxide is equal to 3 over 2, okay? And this is what the mole ratio is, mole ratio. And it's very, very important in stoichiometry, because what if I had 2.35 moles of iron oxide, okay? In real life, you're not always given easy numbers like 2 moles, 3 moles, 7 moles, whole numbers you can work with. Oftentimes, you're given, 2.3, 2.4 decimal-like values. And how do you figure out that? Well, all you have to do is use the mole ratio, right? Let's say it asks you how much carbon dioxide is produced. Well, just find the mole ratio. Carbon dioxide over iron oxide is equal to, well, for every 3 molecules of carbon dioxide produced, we need 2 molecules of iron oxide, so 3 over 2. And how much iron oxide do we have? Well, we have 2.35 moles of iron oxide. And we want to figure out how many moles of carbon dioxide. So we just solve for x, and the value we get is 3 over 2 multiplied by 2.35. And you get 3.53, my bad, 3.53, okay, moles. And this is incredibly powerful because let's say you know you have 2.35 moles. You want to know how much carbon dioxide you will produce. Well, you can figure it out just by using molar ratios. You can figure out that that if you have 2.35 moles of iron oxide, you will produce 3.53 moles of carbon dioxide. And this all just goes down to the simple fact that for every 3 carbon dioxide molecules, okay, let's make this carbon dioxide, okay, for every 3 carbon dioxide molecules, you need to have 2 iron oxide molecules present due to the conservation of mass. Okay, or another question, let's say you were able to produce 10.73 moles of iron. Okay, now you have to figure out, okay, how much iron oxide was there and how much carbon was there. Well, we can figure it out once again by molar ratios. The amount of iron over, let's say, carbon, we want to figure out that first. Well, for every 3 carbon atoms, we will produce 4 iron atoms. Okay, 3 to 4. And how much, and we don't know carbon, so that's going to be an x. The carbon here is going to be an x, but we know how much iron we have. We have 10.73. Okay, so when we solve for x, okay, when we solve for x, we get 10.73 times 3 over 4. Okay, 8.05. Okay, so we instantly know that if we produce 10.73 moles, we don't know how much we had, but if we know that we produced 10.73 moles, we know how much carbon was used up. 8.05 moles of carbon was used up in that reaction. All from the simple fact that for every 3 carbon atoms, you need to produce 4 iron atoms. Same thing with iron oxide, you would do the same thing. You would do the same mole ratio. We do Fe over Fe2O3, yada yada yada, right? And this would be equal to 4 over 2, and we said, what did we say? We had 10.73 moles of iron, so we want to figure out how many moles of iron oxide we have. Let's do another example. Same thing, right? Stoichiometry lets you deal with how much you have and how much you end up with. So one final question. Let's say we had 1.62 moles of aluminum sulfate. Okay, we want to figure out how much hydrogen gas was produced, because remember, for every 3 molecules of sulfuric acid and 2 molecules of aluminum, we need to produce not only 1 molecule of aluminum sulfate, but we also have to produce 3 molecules of hydrogen gas. That's the conservation of mass. If we didn't, then we would have hydrogen mass being lost, and that's impossible. So once again, molar ratios, right? Hydrogen over aluminum sulfate, that's going to be equal to 3, because the coefficient here is 3, and aluminum sulfate 1. Okay, and all this is saying is for every 1 molecule of aluminum sulfate, we will produce 3 molecules of hydrogen. That's all it's saying. Okay, and we need to figure out how many we produce. Well, we produced 1.62 moles of aluminum sulfate, and we don't know, and we want to figure out how many moles of hydrogen we produced. So use your calculator. We get 4.86. Okay, moles of hydrogen gas. Okay, not just moles of hydrogen gas. So there's actually 4.86 times 2 atoms of hydrogen moles of hydrogen atom. Okay. Now, why am I dealing with moles? Because stoichiometry is all about moles, and as you get onto higher levels of stoichiometry, which we will cover in this course, you're not going to be given moles. You might give something like, you have 70.3 grams of aluminum. Okay, what do? You convert that to moles. You might get a value of, I don't know, 1.73 moles. And once you do that, you're golden, because then they're going to ask, okay, how much hydrogen is produced? And you know what to do. You just say the molar ratio of hydrogen to aluminum is equal to 3/2, and I had 0.73 moles. My bad. This is a reactant, so you were given 0.73 moles. You didn't produce 0.73 moles over X, and you can find the moles of hydrogen. Okay. Or another question they might ask is, what mass of aluminum sulfate did you produce, given the fact that you had 1,000 grams of sulfuric acid. Okay, so both of these are asking for grams, but at the end of the day, you still need to convert to moles. You still need to convert this to moles. You can't leave it in grams, because some atoms will weigh a lot more than others. Okay, like just looking at this, I can tell that sulfuric acid per atom will weigh more than aluminum. But so you have so just make sure to convert them into moles. So you would take this, divide it by the molar mass, so using the equation mass over molar mass, and remember N means moles, you get the moles, and from there you use these moles to figure out how many moles of H2, and from that you can use the moles of H2 and multiply that by the molar mass to get the mass. Once again, using the equation mass over molar mass. Okay, and then just multiply by molar mass times N equals mass. Okay, so that's an introduction to stoichiometry.